Hello, everyone. My name is Jeff Hall. I'm the director of Lowell Observatory up here in Flagstaff, coming to you virtually for this installment of the Dark Sky Talk Series. It's always a pleasure to come down to Fountain Hills and do these talks in person. Hopefully, we'll be able to do that again, perhaps next year. But for now, we're going to have to use the old video recording method. And I'm going to talk to you today. This is a two-part talk on two separate challenges to astronomy and dark skies that are coming rapidly to the fore. And one is from the ground and one is from space. And I have a presentation, so I will share my screen. There, that should do it. So the talk is called From LEDs to Satellites, and we are going to talk about ground-based as well as space-based challenges to dark skies. We're really in a kind of a watershed era right now for dark sky protection because of the rapid changes in technology, in deployment of LEDs for outdoor lighting over the past 20 years here on the ground. And now, just now, within the past year and a half or so, the rapid development of large constellations of satellites in low Earth orbit. In a sense, the low Earth orbit environment is in exactly the sort of rapidly changing place that the ground was with the deployment of LEDs coming along around the turn of the century. So we'll start on the ground and talk about LEDs. Now, this is a picture of some highly non-compliant lights up here in Flagstaff that have since been replaced with code-compliant amber lights. This is a classic example of a high temperature white LED. And lumen for lumen, a white LED will increase the sky glow relative to the high pressure sodium systems they usually replace by 50% to 100%. The hotter they are, the higher temperature they are, the worse the impact is. And this is happening all over the world. And you can see this clearly in some of the familiar plots of light pollution contours. So this is the United States. This is from the Atlas by Fabio Falchi et al., published in 2016. And what they're showing here, these contours show that by how many times the local sky is brightened over what the brightness of a pristine dark sky would be. And for the technically minded among you, they're defining that in this atlas, a pristine dark sky as 22 magnitudes per square arc second. And that's a really, really nice dark sky. And so you can see here the amount by which the sky brightness is increased over that. So here in the greens, we're generating as much artificial light as the sky itself. Here we're generating 5 times as much, and so forth. Right around the green to the yellow contour is where it becomes difficult to see the Milky Way. Basically, the Milky Way has been washed out by the ambient light from all of the light pollution. And you can see in the eastern United States, there's enormous swaths of the greens and yellows and even worse, in the urban areas, you're up to 20, 30 times the ambient night sky brightness. So something like 75 or 80% of the population of the United States lives where you can no longer see the Milky Way. And we certainly see that when people come up to Lowell Observatory to view. And because of Flagstaff's dark sky protections, you can see the Milky Way from right here at Lowell and even from right in downtown. And lots of people just don't know what it is because they've never seen it. Here we can see, this is Europe, and we can see the impact of the deployment of white LEDs. So this is the current light pollution situation in Europe. And you can basically see in Europe, there's not much Milky Way viewing anywhere in Europe west of Russia. And then on the right panel, they have modeled what the impact would be with a wholesale conversion of lighting in Europe from the legacy systems to LED. And you can see the dramatic expansion of the red contours here, dramatic expansion of yellow. So this is the degree to which the skies will be impacted by the deployment of white LEDs. And there's some remarkable things in here, like right there. This is Greece and Turkey, so that's the Aegean Sea. there's virtually nothing left in the sea where there's even a dark sky away. There's so much light pollution from the surrounding cities. You can also see all of the, I think these are fishing boats up in the North Sea here. So there's little touches of humanity wherever you look. So this is what awaits us on the ground as we rapidly begin deploying white LED throughout the world. And I'm always careful to point out in these talks, and really what I'm trying to do with this talk is give you some talking points and advocacy points that I have found particularly effective when I'm trying to talk to communities. I know this talk is probably largely preaching to the choir, but you're all trying to make a difference as well, which we greatly appreciate. So, dark sky protection is certainly about astronomy. Here's Kitt Peak, and there's the immense light dome of Phoenix, and you can see Interstate 10 right down there. This is looking north from Kitt Peak. Astronomy and the related optics industries in Arizona, it's a $4.5 billion industry in the state. We are one of the astronomy capitals of the world. It brings good paying technical quality jobs to the state. It's an asset our state can be proud of, and with a tremendously long heritage. Lowell was founded 127 years ago. And so we've had more than a century of tradition in Arizona of exploring the cosmos. But there are noticeable environmental and ecological impacts of degradation of the night sky. A classic example being sea turtles, which rely on glints on the water to navigate out once they hatch on the beach. But if there are lots of natural lights inland, they get confused and go the wrong way. And these slight disruptions to the ecological chain can have real ripple effects. It's a system we want to mess around with at our peril, sort of like the whole climate issue is coming to the fore as well these days. And then finally, human health impacts. So this is a cutout of an email I got back in 2018. I've been participating in a cancer prevention study for quite some time, and they just contact you every several years, every 3 or so years, and ask you a whole bunch of questions about your lifestyle and your diet and so on. Clearly, they're trying to collect lots of data from a sample of however many tens of thousands of people and look for risk factors and mitigating factors for cancers. And in the 2018 study, they added this long section on my daily exposure to light. They wanted to know, what hours do I normally sleep? Do I have a night light in my bedroom? Is there a glowing clock or something? When I'm awake, how much of the day do I spend under artificial light or natural light? It was a detailed section because the medical community is responding to increasing data that disruption of the natural light dark cycle, circadian rhythms, has genuine health impacts and impacts the prevalence of certain types of disease, both mental, diabetes, certain forms of cancers. So whenever we're talking and advocating for an idea or a concept, you need to be relevant to the audiences you're talking to, and lots of people get inspired by astronomy, but lots of people don't necessarily see how the degradation of one of my stellar spectra impacts them. But when you start talking about ecological disruption and impacts on human health, that's a very impactful story wherever you're talking about these issues. So to condense the dark skies into one slide, and what do you do to preserve the quality of the night sky? Well, the one I think everybody knows, full cutoff shielded fixtures so that no light is being emitted above the horizontal. Flagstaff and other communities use lighting zones. The different shaded areas here specify how much illumination can be used per acre. And that will vary somewhat depending on the zoning type. But it's designed to make sure we use enough light, but not too much light. And one way I always like to put this is a dark sky ordinance is not a dark ground ordinance. It's making sure the ground is properly illuminated and we're not having unnecessarily light going up. And then, of course, the one thing that is a little harder to access and explain is spectrum management. And it's often overlooked in dark sky advocacy, but managing the spectrum of emitted light. And we'll talk about this in a few minutes in a little more detail. But that can dramatically improve the quality of the night sky. So to say a little more about the spectra, and this will show you why the white LEDs are so damaging. The top spectrum here, if you think of this as just sort of a normal prismatic violet to red spectrum, this is the spectrum of low pressure sodium. This was the lighting standard in Flagstaff for many years, from 1989 until just a few years ago. And it's the gold standard for dark sky protection because it's basically monochromatic. The entire rest of the spectrum is untouched by this amber light. This is high pressure sodium. There's its spectrum. It's not actually a terrible dark sky light. It's a fairly controlled spectrum, mostly out here in the red. This is what you see. This is in use everywhere. It's what you see when you're looking at that straw yellow color, say at night on a commercial airplane flight. This is very widely in use in cities around the world, except now over just the past 20 years, along come LEDs. And this is sort of the standard high temperature white LED. And you can see it just splatters the entire spectrum, and it's very blue rich, which is ruinous to your night vision. Somewhat better, this is the standard that ADOT has adopted for Phoenix, 3000 Kelvin white LED, better in that there's considerably reduced emission here in the blue, but still much, much, much broader. And so this is why any of these white LEDs are just going to noticeably increase sky glow over high pressure sodium by a factor of 50% to 100%, maybe a factor of 2.5. This LED right here, the 5000K white LED, will increase the sky glow relative to low pressure sodium by a factor of about 8. It's dramatic. And so this is why, this is the reason for that great growth in the light pollution contours you saw a few slides ago in that slide of Europe. Now, what we're doing up here in Flagstaff, and this is just coming to a conclusion, the Street Lighting for Enhancing Dark Skies, or SLEDS project. We've been working with the city for several years on this. Right now, today, or the standard in Flagstaff, we've had about 30% high pressure sodium. And this is, I should be clear, this is for our street lighting system, strictly. It's about 3,700 fixtures, but it will set a precedent for things like parking lots and residential and so forth. So we've had 30% high pressure sodium, 70% low pressure sodium. Low pressure sodium is now obsolete, discontinued. The manufacturers are no longer making it. And so as these fixtures burn out, we can't get replacements. So this really forced us to make a change. Now, what's happening, as we said a moment ago, around the world, this is what the rest of the world is doing. And a lot of these LEDs are these high temperature ones with all of this blue white. Flagstaff tomorrow is, or tomorrow metaphorically, of course, this will take several years to do this retrofit. The new standard in Flagstaff will be narrow band amber LED. And as you can see, that's really a very narrow spectrum. It is the nearest LED analog to low pressure sodium. We will use phosphor converted amber LED for about 30% of the fixtures. As you can see, it's a much broader spectrum again, but none of this short wavelength green to blue. There's really none of that. And this is actually a pretty good answer. The phosphor converted amber is not the official standard. The city wants to use it where they want a little more illumination on the street and where they'd like and higher speed arterials over concerns about safety and just having proper illumination for pedestrian safety. We'll talk a little bit about safety in a minute, because that's one of the important issues we have to deal with in dark sky work. So here's a couple of slides that show what happens when you switch from good lighting systems to white LEDs. So a 4000K white LED spans this whole spectrum. And what you can see is the red curve here. This is from Chris Luganbuhl of the Flag Dark Skies Coalition. That's your photopic response of your eye. This is how this sort of the wavelengths your eye sees during the day. And then at night, you switch from using principally your cones to using principally the rod receptors in your eye, and the sensitivity shifts to the blue. And so the white LEDs, this is why these white LEDs look so tremendously glary and for visual appreciation of the night sky. This is ruinous sky glow because it's right where your eye's becoming more sensitive. Phosphor converted amber is much, much, much better. You can see there's limited emission overall and limited emission where your night adapted eye is sensitive. Narrow band amber, even better. Right here where your eye's response is sort of coming up, so you can still see pretty well. You can see perfectly well under these lights, but it's much less just hammering away at your eyeball than the whites do. And here's what you can achieve with a good dark sky ordinance. This is an all sky view from near Meteor Crater, about 30 miles east of Flagstaff. And so this is going from north to east to south to west and back to north. So it's full horizon. And then from horizon to zenith. So that's the entire sky. And what you can see is it's a beautiful sky. The light pollution, quote, you see in the sky is the light pollution you want to see. That's the Milky Way galaxy right there. And then you can see the light domes of nearby towns. There's Phoenix, 115 to 150 miles away. But check this out. Here's Winslow, okay, with a red and yellow and green light dome. Population 10,000. Flagstaff, population 80,000. And admittedly, Flagstaff is a little farther away, but you've got 8 times as many people. And look at the dramatic difference in the sky glow. And this is all due to strict full cutoff shielding, managing the illumination levels, and critically managing the spectral output of those fixtures. Perhaps an even more dramatic example is right here. These are 2 more all sky projections. Here is Flagstaff from Ashurst Lake. And out here, again, you can see the Milky Way, the purple. This is beautiful dark sky where the purple contours, you're really getting down close to that pristine sky quality in the Falke Atlas. And then here is Cheyenne, Wyoming, a city of comparable size. And this is taken from comparable distance. And so Flagstaff, Cheyenne, and you can see just a humongous difference in the quality of the sky, thanks to what we've been able to do here. So I'll wrap up this part of the talk by just reviewing a few things we commonly hear and a few talking points that you can use in advocating for good dark sky lighting. Dark skies means no lights at all. Where the light police turn them all off, that's a common misconception that we need to dispel. Astronomers like amber because they can filter it out. Nope, we can't filter out any light pollution. We just know it's there and deal with it. Amber has nothing to do with it. If low pressure sodium happened to emit green light, we wouldn't be able to filter that anyway. Somehow, when we were working with the billboard companies on please not putting billboards all over the state projecting light horizontally for tens to 100 miles, somebody had gotten the impression from a volunteer at Kitt Peak that astronomers don't start observing until midnight. So we don't know about that, but you'll often hear the argument, well, curfews will solve everything. You just turn off the billboards at 11, everybody's asleep anyway, so it doesn't hurt the advertising, but it's not true, obviously. Observing starts at or before sunset, even depending on what you're doing. Everybody hates yellow lights. I hear that one a lot, and it's not necessarily true. I know I've certainly talked with some people who don't particularly like the color of amber, but I've talked with lots of people who don't like those blue light headlights glaring in your face either. And then the real big one, more light equals more safety and less crime, which is not true. But that's a very delicate and tricky issue. Safety is a real perception. We don't want people feeling stressed out and unsafe. So you have to kind of take those statements at face value and talk about how good, reasonable amounts of lighting are actually better than overlighting and reducing glare. And the picture at the bottom here is just an example of a before and after retrofit of ball fields in Flagstaff. And you can see, not only can you see much better what's going on, but look how much better the field is illuminated with the downward projecting lights. So here's some really strong talking points. So dark skies doesn't mean dark ground. That's an effective one. And here's one I found to be really effective and crucial takeaway for anyone advocating for amber LEDs. Narrowband amber is probably overkill for communities far from observatories. It's a stringent dark sky light. It is the best possible. But the problem is because of the way it's a native narrowband emitter, and because of the way the LED makes its light, it's not as efficient. So these fixtures, the NBA fixtures, are more expensive to install, and they are more expensive to operate. You don't get as many lumens per watt. So your city's energy budget is not being as efficiently spent. And that makes NBA a very tough sell. And really, it's probably more than most communities need, because PCA, phosphor converted amber, is here and it's viable. These two often get confused and just lumped in as amber LEDs, but there's a big difference in how they work. And the new models of PCA are almost as efficient money-wise as white LEDs. They are an entirely viable alternative for a community to adopt. And the right kind of PCA will not increase the sky glow if it replaces high pressure sodium. Whereas any white LED, you're going to get 50 to 100% more sky glow. Phosphor converted amber, you could make that changeover and stay right where you were. And so it's very important for the dark sky community to be recognizing this, advocating for it, and creating demand, right? Because demand will drive supply. And the more demand there is, the more efficiently and economically the manufacturers will be inspired to create them. So it's sort of a, there's a chicken and egg thing going on here. And it would be very good to get that going. Always frame your interactions as solutions, not problems. It's very effective, I think, to come in and explain, if you're trying to start dark sky interest in a community, explain the difference between these two flavors of LEDs and say, this might be more than you need, but here's a really good other option you could consider. And that way, you're giving people a choice and a menu, and not just coming in with a my way or the highway. And that generates much more listening and more favorable responses. And then finally, we have to acknowledge that we have to be respectful of people's perceptions. I think we have 2 million years of evolution of being afraid of the dark, and getting comfortable with lower illumination levels. It can be done, but people's innate nervousness, I think, about being in the dark and some of these misconceptions about safety and crime, they're very difficult to dispel. And you just have to accept perception. You can't just say, well, your perceptions don't matter because the data say otherwise. It's not a good way to move forward. All right, so that's the situation with LEDs, and I'm going to switch now up about 300 miles above the ground, because we've got this worldwide situation where if everybody could go to either, if they must use white LEDs, very low temperature ones like 2400 even. I think 3000 is too hot, too high. Now we've got the situation in Earth orbit. So we're going to change gears here and talk about what's going on in space and what we've been doing over the past now about 2 years since the launch of the first tranche of Starlink satellites. And I refer to this as the industrialization of space because we're there and it is very sudden. So, and to frame this, 20 years ago, LEDs rather abruptly became viable and economical for use in outdoor lighting applications. And boom, you had this raw, rapid deployment. Now we're at the stage where technology has advanced to the point that nimble private sector companies like SpaceX and Amazon and Blue Origins and OneWeb and Virgin Galactic can access space, and they're going to do it, and they're going to do it fast. And there's going to be an explosion of hardware up there that's going to transform the landscape over the next 10 to 20 years. And this is a at this point almost notorious image captured right here at Lowell Observatory about 3 days after the launch of the first 60 Starlink satellites. And they happened to fly right through this little galaxy cluster we were showing in one of our public programs. This is not taken by a research telescope. This is just a little 8-inch celestron, or maybe an 11-inch celestron that we were using for the public program. And there you go. There's Starlink in a very tight cluster. This was sort of in its string of pearls phase. So the satellite constellations that companies are planning to launch, and these are, as you probably know, these are for global broadband internet connectivity. This is a perfect storm for astronomy. And it comes along 3 main lines. First of all, these satellites are bright. Okay, in their parking orbit after they launch, they sit them in a parking orbit for a while, fairly low, so that the orbits will precess and get them into the orbital plane that they want to get the, and then they put them all in different planes to get the global coverage they're looking for. Visible to the unaided eye, as you probably know, depending on how good your eyesight is, you can see down to magnitude 5.5, magnitude 6. Really eagle-eyed observers with much better eyes than mine might be able to see 6.5, maybe even 7. They're on station, and largely because of a lot of the work that SpaceX has been doing over the past 2 years and a lot of the interactions between astronomy and SpaceX, they're probably going to be about 7th to 9th magnitude. So not visible to the unaided eye. And you'll occasionally hear hyperbolic statements. Elon Musk is going to create 10,000 new stars crawling around the sky, and they not visible to the unaided eye. They're going to be fainter than that. So brightness is a concern, since you can see them in the parking orbit, and 7th to 9th is ferociously bright for a research telescope. The sheer potential number of them, the FCC filings are up in the many tens of thousands. And to give you an example of just how fast this is changing. So right now, there's about 2,500 functional satellites, 2,500 dead ones. There's a few tens of thousands of pieces of this junk, larger than about 10 centimeters. There are actually only about 200 satellites you can see with the unaided eye. The Hubble Space Telescope, the International Space Station are prime examples of very bright ones. And most of the other bright ones you see tend to be, they're big. They're like dead Russian rocket bodies or something floating around up there. In fact, most of the ones, when you see a satellite cruising across the sky and it's really bright, it's probably some sort of rocket body. And then in addition to the sheer number, right, we're going potentially from a few thousand to 100,000, just like that. There's basically no regulation, and I call it a wild west up there. And apart from having to get the FCC approval and all of that, they can pretty much launch where they want. And space is going to get really crowded, and there have already been a couple of collision avoidance events with some of these satellites. So SATCON 1, we've hosted 2 workshops to deal with or to foster communication between the satellite industry. And this is a slide from this slide is a little out of date at this point. SATCON 1 was 29 to 2 July in 2020, and I'll talk a little bit about what we concluded, and the satellite companies participated in that. SATCON 2, this is a slide from a talk I presented in the spring, and so this workshop actually occurred in July, just less than a month ago, in the middle of July 2021, and I will talk a bit about the conclusions there. So in SATCON 1, we considered all the kinds of science cases that in astronomy that satellites could impact. And as you can see, just about everything, right? from extragalactic imaging, near-Earth objects, looking for potentially hazardous asteroids, exoplanet transits. We considered, citizen science, amateur astronomers, stargazers, they are impacted. A really big one is right up here at the top. These rare transients, these events that come and go. Because this is what facilities like the Vera Rubin Observatory are specifically going to be looking for. And then you're going to have satellites flying through. So you have a lot of issues. So we commissioned 4 working groups to look at different aspects of the satellite problem. One of them was the observations working group. Lori Allen is down at what is now called NSF's NOIR Lab, the National Optical Infrared Astronomy Research Laboratory. Used to be NOAO, they run Kit Peak. And this is a simulation of what over a 10-minute exposure, the sky over Vera Rubin Observatory in Chile. This is what it would look like. Every yellow streak is a satellite trail, and this is, I believe, this is modeled for about 48,000 satellites. And you can see near the horizon, there's just a blizzard of trails. There's virtually no part of the sky that is not impacted over a 10-minute exposure, except right here, and this is where the Earth's shadow kicks in. And that's basic rule of thumb. You don't, to see a satellite, you have to be in the dark, it has to be in the sunlight and reflecting sunlight to you. And then these are observations of Starlink satellites. This is from about a year ago, and ranging from about 4th to 7th magnitude. So there's a lot of them that are kind of down here at the very low end of visual brightness, and then a lot more that are a little bit fainter than that. And SpaceX has continued to work on design changes to their satellites that have started to push that a little bit fainter. But you can see that here they're getting them down to about 7th. And I'll tell you what our recommendation was in just a moment. So here's your impact from the observational standpoint. This is what the sky potentially looks like to a research telescope. The simulations working group looked at, what if you had so many satellites at such an orbit, what are we going to see? And Pat Seitzer at the University of Michigan is sort of the guru for all of this. And here's an example. Again, this is the skies over the great observatories in Chile. 10,000 satellites at 500 and 1,000 kilometers. And here's where you get a little bit of a counterintuitive result. We actually found it's better for the operators to fly low. The satellites are a little brighter, but their visibility goes way down. This is time, right? So from sunset to sunrise, you can see with 10,000 satellites at a 500 kilometer orbit, you're going to have about 40 of them sailing around, and then that's gradually going to go down to 0. And it's going to be 0 when in the dead of night, because the satellites are mostly going to be in Earth's shadow. And then you'll start to see more as you get closer to sunrise. But at a 1,000 kilometer orbit, you've got well over 100, and they're visible all night. Even at the darkest part of night, you've got about 40. Now imagine if instead of 10,000, you had 100,000 satellites, multiply by 10. 1,200 satellites. They're going to be everywhere, and even several hundred still in the dead of night. And that's why the plot on the last page is just filled with trails when you integrate for 10 minutes. The Mitigations working group began looking at, how do we darken the satellites? There's 2 ways to approach this. Operators can work to make the satellites darker, and SpaceX has been investing a lot of time and money to do just that. And then there is a huge unfunded software mandate on astronomy, because this is a simulation of what one of the Vera Rubin Observatory images might look like. You've got this saturated trail where the satellite just went through the image, and then all of these subsidiary crosstalk trails, and removing all of these from the data. Well, this can't be removed. All you can do with that is just mask it out, and you just lose that data forever. With the other trails, you've got to find a way to remove them that's consistent and believable and accurately recovers the data underlying it. And it's going to be very difficult to do. So as you can see, SpaceX has made a couple of efforts to darken their satellites that have been fairly successful. The very first one, which we didn't think was going to make that much of a difference, and it didn't, was the so-called DarkSat, and it picked up about a magnitude. They're just, painting their satellites dark. They have since redesigned satellites that actually have visors on them that block the sunlight from getting to the reflective surfaces in the first place. And then the metrics working group was looking at, what do we need to do? What are the parameters we need to address to preserve the observing quality at some of these massive facilities coming online, like the Vera Rubin Observatory. And we're entering the era of 30-meter class telescopes, the 30-meter telescope itself, the Giant Magellan Telescope, the European extremely large telescope. We found wide field and twilight programs will be severely impacted. We want the operators to fly low, but there is no way to eliminate the impact on astronomy. They're going to be there, and we're going to have to figure out how to deal with it. So the recommendations we came up with were we need more robust software and predictive tools. We need to understand how to deal with the satellite trails in a holistic way, in a unified way as a community, because if you have 20 different people reducing different sets of data, how do you know it's consistent? How do you know that if you're seeing changes in the universe, it's not part of the data reduction and satellite trail removal, but it's actually a real physical phenomenon? Very difficult. For the operators, we recommend they design their satellites from the ground up to be as non-reflective as possible. This is a bidirectional, the BRDF measurements, bidirectional reflectance function. You can start doing these measurements as you're designing the satellites. The metric we come up with for brightness is fainter than 7th. That gets us to the point where some of those subsidiary trails in the images can be masked out. Minimize reflection in the direction of observatories. And here you see this, these are pictures from SpaceX itself of the DarkSat, where some of these bright surfaces have been painted dark. That actually harms the satellite because it absorbs light, and it's not as thermally well controlled. And then over here is the visor sat, where they've deployed these shades to prevent sunlight from hitting the satellite in the first place. And finally, we thought there are things astronomers and satellite operators can collaborate, like a comprehensive satellite observing network. This is an excellent opportunity for citizen science. We need thorough observations of satellites to see how bright they actually are. And it's a very complex function of their attitude, what's their elevation above Earth, what's the range, how far away are they, how are they oriented, what are they made of. The companies will need that feedback. And so we need a global observing network. We need better positional information so we can predict better where the satellites are, because research telescope standards are stricter than the standards the operators have used, and adopt a new standard format for the satellite positions, the ephemerides, beyond the present TLEs, or two-line elements, which are the sort of standard strings of characters that tell you what a satellite's orbit is like. We need to improve that along with uncertainties. So the reports of our workshops, I've got the links here. The SATCON 1 report is complete and available. The SATCON 2 report will not be available probably until about the end of September. The working groups need time to finalize their reports, and then we need to write an executive summary. SATCON 2 was focused on basically how do you take all these recommendations from SATCON 1 and what do you need to do to implement them? How many people, how much money? And one of the fundamental things we're going to be recommending is the creation of an international multi-stakeholder center for putting together this observing network, for encouraging much broader participation from environmental and indigenous communities, as well as industry and operators, and space policy and space law, because one of the SATCON 2 working groups concentrated on what are the policies and procedures we can put into place that are agreeable to everybody, and that would sort of get things a little better under control up there. So we are in a, as I said at the start of the talk, this is a watershed era. From the ground, you know, we see the potential for a doubling of sky glow due to the deployment of white LEDs. You know, they can be retrofit. You know, fixtures have finite lifetimes. So constructive advocacy about the virtues of white and amber LEDs is imperative. And the principal takeaway points there are, if communities are going to insist on using white, you push that color temperature down as low as possible. 4,000, 3,000 is still too high. 2,700, 2,400 is better, you know, and you know, I know, you know, Phoenix is using 2,700s, for example, after lots of urging by dark sky advocates in the area in its street lighting system. And you can tell the difference between the, you know, surface streets in Phoenix where they're using 2,700s and the interstates where ADOT is using 3,000s. There is a noticeable difference, and the 2,700s are better. On the amber LED front, the understanding the difference between narrowband amber and phosphor converted amber is critical, and explaining the fact that PCA, the phosphor converted amber, is becoming a quite viable solution. Then from space, again, we can fairly say kudos to SpaceX. They have invested a lot of time and money in redesigning their satellites. Amazon, OneWeb, other companies are getting engaged, and I hope that sort of these big three will set a precedent, because it's not just broadband communication that people are going to use low Earth orbit for. There are Internet of Things applications, you know, just you name it. There are a lot of reasons that people might want to launch large satellite constellations, and you know, countries all over the world are going to do this. So collaborative development of policy is imperative, and we are hopeful that the SATCOM2 report will provide some grist for documents that can actually go to, you know, the UN, which is the international body that can sort of address this. The United States cannot do this in a vacuum. So it's a really interesting time, and I'm going to stop my share there. Yeah, really interesting and busy time to be in the business of dark sky preservation, and more than ever, the interest and advocacy of broad swaths of the populace is very important. You know, at SATCOM2, some of the most interesting talks were with, you know, members of indigenous communities and some of these underserved communities that SpaceX and companies are trying to serve, you know, with broadband internet. And that's a laudable goal. You know, there are many very isolated areas that really could benefit from fast internet, and you know, for educational purposes, for emergency services, you got to contact somebody. So yeah, this is, you know, this is a reasonable thing that Elon has decided to do. At the same time, the members of the indigenous communities, you know, we're also, remember, you know, we tell stories in the stars too, and you know, this is part of our cultural heritage. And you know, come talk to us. You know, don't tell us what we need. Come to us and ask us what we want. And there are lots of just very interesting viewpoints like that I hope we've started a good conversation. And I hope the new center, when it's up and running, will allow us to address. So that's kind of the situation in a nutshell from the ground and from space. Really appreciate everybody's interest and engagement, and hope you've enjoyed the talk and got some useful talking points. And hopefully we can do this in person next year and have another one of those nice star parties on the lawn outside the community center down there in Fountain Hills. So until then, when hopefully we can all get together again, thanks much, be well, be safe, and hope to see you all in person soon.